start my recording. And so again, we know that it has a horizontal tangent. The derivative is equal to 0. And what do I mean by that? So today we're actually going to look at the derivative as a function. So there is a reason we write it as f prime of x, in that you can literally graph the derivative. So when I say that the derivative is positive, for example, we're implying that the graph itself of f prime is above the x-axis. Likewise, I could expand that. If I'm saying that f prime is negative, that literally means the graph of f prime is negative. And then if I say that f prime is 0, that means that the graph of f prime is on the x-axis. So that talks about the increasing and decreasing nature of f. We can also talk about what happens when f itself is concave up, concave down, or neither. If f is concave up, then we know that the derivative is increasing. The slopes are increasing. We learned that if f is concave down, then f prime is decreasing. And then this last one we haven't saw too much, but basically if f prime is not increasing or decreasing is really when it has no concavity. Well, what does that look like when it's on the graph? If your function is concave up, concave up or concave down, then f prime is going to be constant and horizontal. And so we're going to pull all this together, and the notes today, really for today and tomorrow, are going to look at two different things. For the first half, I'm going to give you a graph of a function, and we're going to draw a possible first derivative of that function. And then the second half, the notes kind of go in reverse. We'll look at the first derivative, and we'll draw a possible function based on the first derivative. Since we will be drawing graphs, I do want to kind of talk about like just some weird things that can happen when we're looking at these graphs. So the first kind of weird thing we need to be careful with is when f has a cusp. So we know like a cusp could be when you're coming in at a curve or more at an angle. We know that when the function has a corner or a cusp, that the derivative is undefined. Well, what does this look like when we graph it? It is going to look like a jump, and we need to make sure we look at the actual slopes. And we'll see what that looks like when I start graphing it, but what I mean by looking at slopes, at a corner or a cusp, you have a sudden change from a bunch of negative slopes to a positive slopes. So when you graph it, you'll basically have some slopes that are below the x-axis, and then they immediately jump up to have some slopes above the x-axis. Next kind of weird thing that can happen, if your function has a vertical tangent line, then f prime is also going to have some sort of vertical tangent. It's not necessarily going to be the same kind of look. You just want to, again, look at the slopes. Like if the slopes are positive, draw them as positive slopes. If they're negative, you're going to draw them as negative. And then if f has a discontinuity, then f prime itself will also have a discontinuity. So what do we mean by graphing f prime? F prime we know is the derivative. And so when we're graphing it, when we graph the function f, we have like a t-chart where we're plotting the x's and the y's, and those form your coordinates. When I go and plot f prime, you're still plugging in coordinates, but in this case, your y's are going to represent f prime, which is going to be a bunch of slopes. So if you want to think about the coordinates, you're literally plotting like if the slope of the function is 3 when x is 4, then literally at 4 you're going to plot at the point 3. So we're going to be plotting really a bunch of slopes, and that's what's going to create our function. And so I do have two examples of each type. One that's kind of like an easy one, and then one that's more of the calculus level. So this is the handout that I definitely want you to be able to refer to if you can, that's already in OneNote. And basically this will be something that I would hope you can do kind of fairly quickly. But at the same time, I want to make sure I do it slowly enough that we kind of make sense of what's happening. So looking at this problem, this is the graph of f. So this is like the original function. And I want to sketch a graph of f prime. I literally want to draw a graph of what all these derivatives look like. And I chose this one to start off with because it is a piecewise function, but it has a lot of straight lines in it, so that's going to make plotting the slopes easier because we know already how to find the slopes of straight lines. Like we know how to count rise over run and find those slopes. For example, like the easy ones, all those horizontal segments have a slope of 0. So we know that when I'm graphing a sketch of f prime, I know that I'm graphing a bunch of slopes. I'm going to use the variable m for slopes, and that's commonly what we use like in Algebra 1 and stuff. So I just want to find the slopes of these lines. So when I go to look for my slopes, like this second section that's horizontal, we know the slope is 0. Starting at x equals 0 to 3, I know the slope is 0. And also from 3 to 6, the slope is 0. Well, what does that mean when I say the slope is 0? If the slope is 0, then that means the derivative is also going to be 0. These other pieces, I do just want to go ahead and find the slopes. Again, we can find slope by doing the rise over the run. I should have labeled probably some more coordinates on here so it'll be a little bit easier. Like an easy one to kind of count is the third segment starting at -3. And we can see we kind of go down 1 over 1, down 1 over 1. So it has a slope of 1. The one starting when x is 2, we're going up to over 1. So it's going to have a slope of +2. It's increasing. And then the very last segment we see, again, up 1 over 1, up 1 over 1, it has a slope of 1. This first one, I should have put more coordinates on it, but I'm going to estimate the slope to be, just for the sake of it, -2/3. So obviously, if you do this on your own, you find the slopes of each segment. Go ahead, who's ever asking a question?
Shouldn't the slope of the second one be -1?
Yes, I wrote +1, and that's a big mistake of mine. Thank you, Matthew. -1. So again, I found them, but you can find just as easily the slopes of those segments. And again, big calculus concept is the derivative represents slope. So I'm going to graph in the actual derivative function. I'm going to use my orange pen to do it. I'm going to do the easiest parts first. So when we are going to graph f prime, like the x values are still x values, but now you want to think about like the y-axis showing you what the slope is at those values. For example, between -5 and -3, all those x values have a slope of 0. And I'm going to put open circles at the end of that because we know that the derivative cannot exist at a corner or a cusp. All these segments have corner or cusp, so we know there can't be a derivative at those corners. Same thing starting at 0, like the slope at right after 0 is 0, the slope at 1 is 0, the slope at up to 2 is 0, and then we stop right at 2. And then likewise for the segment that's also horizontal, it has a slope of 0 all the way across as well. So again, that part I did in orange is representing the slope of that graph at those x values. This first segment, moving from left to right, it has a slope of -2/3. So I know that every x value along that interval has a slope of -2/3. And just kind of estimate where that would be at. Probably should be a little bit further down, but we'll say -2/3. That third segment, we know that every single point has a slope of -1. So I'm going to say every single x value on that interval also has a slope of -1. Starting at x equals 2, every single point has a slope of 2. And at the very end, every single point for that last segment has a slope of 1. So again, what that orange graph represents is if you could read that, if you didn't have that original function in front of you, you would be able to say like, hey, what's the derivative at 5? And you can look at that orange graph and see, oh, well, at 5, I can see that the derivative is equal to 0. So I would know that the graph is horizontal at that point. So it's just another way of interpreting the graph by using its derivative. I think the straight line segments are definitely the easiest ones to deal with because we know clearly how to find those slopes exactly to be able to translate it from f to f prime. Before we do one where we have to estimate it a little bit more, are there any questions on this one that I should go back and explain a little bit better? All right, so the next example I want to look at is underneath that one if you're looking at it under OneNote. So it is a cubic-ish function. I know it's a cubic, but it's a cubic function. And this is, again, the graph of f. And we want to graph f prime. And I'll do it again in orange once we get there. So we want to find what this graph of f prime looks like. And I kind of take it piece by piece and do the easier parts first. For example, I know the easiest parts, at least for me, are going to be where the derivative is equal to 0. What will be one x value in this graph that would have a derivative of 0?
-5.
-5, we can kind of see horizontal tangent there. And then following what Anna said, we know that there's going to be another one at the other horizontal tangent at 9. So what does that mean? We know that horizontal tangents have a slope of 0. So that means at -5, the derivative is at 0. Also at +9, the slope is at 0. When I say the slope, I'm really referring to the derivative. And then I see there's some other things happening as well. So I see I have an increasing section of the graph. The graph is also increasing after 9. And then the graph is decreasing between -5 and 4. So I want us to think about what it means to be increasing and decreasing on f. When f is increasing, what is f prime going to be? So when
Positive.
f is increasing, f prime exactly would be positive. So if I kind of think about this as little boundary points, and the dotted lines are really just to kind of help you see it. When f is increasing, I know that f prime is positive. And when I say positive, it's going to be positive values above the x-axis. When f is decreasing, f prime is going to be negative below the x-axis. We, of course, know that when it's 0, it's on the x-axis. And so this last part is also increasing, so f prime is going to be positive and back over the x-axis. Well, we know that a graph doesn't have to just increase or decrease. There's also a bend that is important to us. So if I'm looking at this graph, moving from left to right, I see that it's starting off being concave down. It's making that umbrella shape. And we're going to eyeball it now. We don't really know what the function is, so we just need to eyeball it. But if you were to pick an x value, at which x value do you think does it appear to be switching between concave up and concave down?
9.
I look a little bit less than that. Like to me, I'm kind of seeing around like 1 or 2. I'm going to put a point there in red. Kind of to the left, if everyone can kind of look to the left of that red dot, it looks to be concave down. And then starting to the right of that red dot, it looks to be concave up. So remember, like a umbrella is concave down, a bowl is concave up. Another way to tell if you were to draw it in a tangent line, if it's concave down, your tangent is above the function. And if it's concave up, any tangent line you draw ends up being below the function. But we can see that there is like another dividing point at this point on the graph where we have its concave up and concave down. So let's also remind ourselves, when f is concave down, what is f prime going to have to be doing?
Decreasing.
Decreasing. And then the second half of this function, we see f is concave up. If f is concave up, then f prime has to be increasing. So within each section, I kind of look at this graph as having 4 sections. There's kind of 2 things happening at once, like f prime can be positive and decreasing. It could be negative and decreasing, negative and increasing, and then again, positive and increasing. So I am less picky about you finding the exact slopes. Like if I want to be particular, I would like look at, say like, oh, at x equals negative 11, that looks to be exactly a slope of 5. I'm not expecting you to do that. I just want to make sure we can get the shape correct. So I'm going to start drawing in the derivative in orange, moving from left to right, and kind of explain where my shape is coming from. But again, I care more about like the shape and less about the actual accuracy of the y value you're plotting. So starting on this far left-hand side, I see my graph is pretty steep and increasing. And I know that it is going to be increasing basically starting with that function. So I want to draw something where f prime is positive, but also decreasing. So I'm going to go ahead and draw that in. So I'm starting up here. Again, the orange is above the axis, so I know that my slopes are positive. It's decreasing because it's concave down. I'm using that x-intercept as kind of a goal to shoot for. This next section, the function is decreasing, so my derivative is negative. The function is concave down, so I know that f prime is also still decreasing. F prime is going to stay negative in this next section, but since it switches to be concave up, it's going to start increasing. It's still below the x-axis because I have negative slopes. I hit my x-intercept. And in this last section, it's increasing, so the slopes are positive. It's also concave up, so the graph is increasing. So that graph in orange is the derivative graph. And you can kind of see how it matches up. Now, obviously, I've done this multiple times, so I kind of knew exactly what it would look like. I care more about can you get the shapes correct. So if you have something that, if you drew something that even resembles what I have in orange, I would give you credit. Because what I'm looking for is, have you clearly marked where the derivative is 0? Those are the x-intercepts. Is your graph positive? Is your derivative positive when your graph is increasing, negative when your graph is decreasing? That's another thing I'm looking for. And then I look for whether it's increasing and decreasing correctly. So this derivative, the first half was decreasing because the original function was concave down. The second half, my derivative was increasing because the original function was concave up. So we actually see like a low point on this graph was where that concavity changed on the graph. I feel like that's a lot to take in at once, but are there any questions you can formulate right now and ask? Awkward lag. All right, then we'll just move on to the next one. So those are 2 examples where we are drawing the derivative based off of the function. The next page you have in OneNote in your notes, I actually took those same graphs, not because I'm lazy, but because I want you to be able to kind of compare some differences in them. And for these, we are going backwards. So if you kind of look at it, I wrote it out a little bit differently, but we are going from f prime to f. So yes, these are the same graphs, but this time we're looking at f prime, and we want to draw the f that we see. And so we do have to approach it a little bit differently. Now, some things about moving backwards. When you're looking at the graph of f prime, if you remember when you think about that chart we filled in, if I just give you information about f prime, we don't exactly know like where the function is. Like it could be above the x-axis, it could be below. So when you're going from f prime to f, the specific y values don't matter. However, the general shape does. So the specific y values don't matter. the shape does. Also, like corners or cusps in the function and the derivative don't really affect what we see on the graph. And I'm going to write that down to kind of show you what that means when we look at it. So when we're looking at this problem, I do think this is the direction that some students have like more trouble visualizing. So I'm going to try to break it down piece by piece. What I want you to kind of think about right now is you are looking at f prime. So you're literally looking at all of the derivatives. So for example, if I'm reading this graph, we see something like what's f prime of, and I'm just making something up, -4. Well, f prime of -4, we can see on the graph that is at 1. What does that mean is literally on this graph of f, which we don't know what it looks like right now, it needs to have a slope of 1. Likewise, if I say, what's f prime of +4? We see f prime of +4 is at 0, so I know that the graph there is going to be 0 or perfectly horizontal. So when I go to graph a problem like this, the first thing I like doing is kind of dividing it into all the different sections I see. And to me, sections are going to be whenever it changes directions or crosses the x-axis. So this actually has like a lot of different pieces going on. Don't have to do the dotted lines. I do this mainly just for like the first few times when I'm teaching the problem. Obviously do it if it helps you visualize it. But to me, those are the sections I personally see on this graph. And I kind of go and I want to figure out, hey, what is f doing on this graph so I can even draw it? Like I want to figure out what my function f is doing. So we're looking at the derivatives. And the first thing I want to figure out is, hey, let's figure out if this is going to be increasing or decreasing. Moving from left to right, this first section, starting at x is -8 and ending at -5, this is above the x-axis, so I know that it's positive. So I know that f is going to be increasing because I visually see positive slopes there. All those x values have a positive value attached to them. This second piece, it's also going to be increasing. It's a little bit of a special case. I see it's perfectly flat because I know every piece in that section will always have a slope of 1. So when I draw my f, every x value between -5 and -3 is going to have a slope of 1. We have it still increasing between -3 and 2. At 2 is a big deal. That's where we have a horizontal tangent line because that's where the graph is hitting the x-axis. The graph is going to start decreasing once it goes below the x-axis. So the next 2 intervals after that are also still decreasing. The one from 0 and 2 is kind of an important one because it's horizontal, so I know that the slope is not 0. The slope is always going to be -2. So when I go to graph that one, I always want to make sure that it has a slope of -2. The next section starting at 3 is kind of weird. It always has a slope of 0, so it's not increasing or decreasing. And then this last one is above the x-axis again, so we will be increasing. So those are kind of what the graph is doing. You can kind of imagine, all right, so it's going to start increasing, then decrease, then have this awkward slope of 0, and then increase from there. Any questions on how I determined where the graph was increasing or decreasing before we talk about the concavity? All right, so let's go ahead and talk about the concavity of f. We know that when the derivative decreases, the function's concave down. When the derivative increases, the function is concave up. So this first section is decreasing, so it's concave down. Second section is not increasing or decreasing. There is no concavity, which makes sense. If it has a constant slope, it is going to be linear. The next section, the derivative is decreasing, so the function is concave down. Next section, the function is still decreasing, so the derivative is decreasing, so the function is concave down. We have another linear section. Then starting at 2, the derivative increases, so we're being back at concave up. We have another linear piece, and then the very last segment, the derivative is increasing, so my function is going to be concave up. So you can kind of see within each section, we have like when is it increasing and what is the concavity. Again, the specific y values do not matter, so you just want to like pick a y and then just kind of continue. And the reason why the y's don't matter is like we have no way right now to figure out what it is. Like it just says, I know the graph is increasing and concave down, but I don't know where to start it, so it really doesn't matter. I care more about the shape that we're going to draw. So I'm going to work from left to right and kind of go slowly and describe it. I do see that I'm increasing basically from -8 to -2. So I'm actually going to start fairly low on the graph just so I don't run out of space. But again, we can start really anywhere. So this first section is increasing and concave down. Then I hit a linear section that has a slope of 1. I'm just going to estimate what that looks like. Next section is increasing and still concave down. Now it's below the derivative is below the x-axis, so I am decreasing and concave down still. Then we have m is equal to -2, so kind of like another linear portion. Then we have slopes that are still negative. And so we want to draw it as decreasing but concave up. We have a slope of 0, so we have a horizontal section. And then we have positive slopes, and the graph is going to be concave up. So that orange graph is like a rough estimate of what this one looks like. Again, we do have some weird like linear sections on the graph, whether mine look perfectly linear or not, because I'm drawing it by hand. But those parts I highlighted are perfectly linear, and hopefully you can kind of see like whenever your derivative is going down, we have this concave down bend to it. Whenever the derivative is going up, we have this concave up bend in looking at the graph. Any particular questions on that one for me? All right, so I'm going to stop notes here because this is not a topic that I want to rush. So tomorrow what we are going to do is we are going to look at this second problem. It'll also just be like kind of a good review of how we interpret going from the derivative to the function. We'll also talk about justifications when it comes to these problems. Calculus is very specific about how we justify our answer, and there's certain ways I want to actually teach you how to justify an answer for this. But that's where I'm going to end today's notes. Continue working on iReady if you haven't finished it. Remember, that is a county requirement.